Okie doke. So this video is the follow-up to the previous video I just did in this series about the AI chatbot. So if you want to see the demo of how this works or what it can do, please check out the previous video, which I'll eventually link to this one. In this video, I'm going to deep dive into why I used Kaggle.com specifically and why I use Jupyter notebooks. As well as I'm going to step through every cell in the Jupyter notebook that I created as the data loader or data workbench, if you will. I've also open sourced this now. And I'll also talk through kind of what I learned in the course of just building this application. The reason I built this application was to intentionally encounter the tools, the workflows, the issues, and problems and obstacles that arise in trying to build an AI chatbot that can answer for any arbitrary corpus of knowledge factually and as an expert on that knowledge. So that's what we're going to do here. So if you've not used Kaggle before, it's a pretty amazing resource. They have a lot there, so I'm not going to do it justice. There's you can create arbitrary Jupyter notebooks on it. They have data science competitions. It's a great place to learn. I particularly enjoyed using it for this project because it was easy to just, quickly create new Jupyter notebooks and run them here. There's support for really great features such as secrets, right, which I talked about briefly in the previous video, but just as you have lots of other platforms that mimic this or have this pattern where if you have a sensitive secret, you store it somewhere securely. And if you're familiar with AWS, that might be AWS Secrets Manager, and then you reference that secret with an ARN or an Amazon resource name. It's sort of like a key. In this case, we're doing something similar where we're storing, by way of add-ons, we're storing secrets, my OpenAI key and my Pinecone API key in Kaggle secrets, so they're secured in the platform. And then within my actual source or my notebook, I can just reference those secrets. I can get the secrets client and then get the secret by name. And what that allows me to do is reference this throughout my code, which I eventually open sourced and knew I was going to open source without fear of leaking one of my private keys. So highly recommend doing that. And you can take a look at the open source notebook if you want to lift that code. Let's take a quick overview. I'll just scroll through this doc, the whole notebook, and we'll talk about what it's doing at a high level, and then we'll step into each cell. So at a high level, this is setting up OpenAI and the Pinecone client, loading the secrets that I just talked about, so the OpenAI API key and the Pinecone API key. In the next cell, we install requests, beautiful soup, and langchain, which we're going to use to parse the information from our target wiki, and then also set up a text splitter that's going to do all of the chunking that we need. So maybe before I get too deep into here, I'll also talk through the data source that I ultimately found and settled on. And if you look here under the seasons tab, and we look at season 1, for example, it's this sort of outer landing page. And then from within here, you can go to each individual episode page within the season. And so what this function is doing, this get summary paragraphs, is reading all of the paragraphs underneath this summary header. And then as the note here mentions, once I got a little bit further along in processing the various seasons, I found that the HTML here is non-uniform, which is very typical across websites. So this summary data that I was interested in could be called alternately summary, plot, or synopsis. And so what this code is doing is using beautiful soup to essentially try all three until it finds the paragraphs that it needs and returns them. This is another utility function. This is writing the episode summary to a file. So we'll talk about why I decided to do that in a little bit. Or we can just talk about it now. So I decided to write all of the episode summaries to a file for a couple of reasons. One, it's really easy to debug, right? As soon as I write this content to a local file, it's easy enough to spot check that file even within the notebook itself, because as we see here, if we look at the saved output from this version, which I've already committed to GitHub, you can see I just wrote myself this little debug phrase to say write episode summary to file, wrote file name. So this means season 2, episode 1, title is the Dundies.md for Markdown. And then within Kaggle or within Jupyter Notebooks, you can inspect anything that's in the input or the output of the notebook itself. So it's really easy to just quickly download a Markdown file, make sure that all the content was there as expected, and the code to do it is pretty simple. Okay, so we talked a little bit about the structure of these URLs, how there's an outer season page, and then there's inner episode pages for each episode. And so what I'm doing in this loop is right here is in each of the seasons that have been defined, which is right here. So you'll see that I came up with this simple data structure. It's just a nested dict. So there's the outer keys are just the season numbers themselves, and then they have a list which is full of the URLs to the individual episode pages. So this is quite simple to iterate through in Python. So just for season and season, get the URLs, and then for each of the URLs, essentially format the information that's needed in order to call get summary from wiki page. And then get summary from wiki page is what we've already looked at. So that's gonna go and get get summary from wiki page is actually right here. Okay. So this is the function that will fetch the HTML from the episode page itself. So at this point, we're already in the URL. We have the URL for the inner episode page. And one of the things that we need to do is just make sure that we get the right episode number. That's always going to exist in this little data block over here, or the sidebar. And the sidebar has, it doesn't look like it, but that's an H3. And it has a particular class, so it's easier to kind of narrow it down even more. And then we need to also look through all of the H3s that were found to make sure that the text is literally episode. And then if that H3 is episode, then we know that the immediately next div element is going to be the episode number, and we can just get the text on that. There is a slight wrinkle, of course, as there is in all data processing ventures. Wouldn't be complete without one. I'm trying to think of a good example. I think season 3 has one. So there's these compound episodes as well. And what a compound episode looks like is this, where the episode number itself is actually a composite of 2 numbers. So it's a string that is 10 /11. And if we look at it here, the episode is 10/11. So in this case, I decided that since we're just writing flat text or markdown files locally, it's simple enough to just replace that hyphen when it's found with and slug, basically, and these underscores. And so that just makes it easy for the title to still be written to a markdown file and then read out without dealing with any like spaces or anything like that. But essentially denoting the fact that one episode is really a larger conglomerate episode. That was really the only wrinkle that I encountered in parsing all this wiki information. So those are the main functions, really. This one is pretty simple. We talked about it, just writes the episode to the file name, and it creates that file name, which is season episode slug. And that's why the files come out as they do. We process this in a loop, and at the end of this loop, we have a markdown file, just as shown here. For the other reason it's nice to have a single output line for yourself is just to be able to quickly spot check, sanity check, and be like, okay, every season and episode is accounted for. Once that's done, we can start using langchain. So langchain already has support for what are called document loaders. There are a ton of different document loaders. If we were to look here, and so essentially, as the docs explain, there's langchain support for both TypeScript or JavaScript and Python right now. but document loaders make it easy to create documents from a variety of sources. So if we look at examples, we'll probably find a couple. Here's some file loaders, right? So anything from CSV files, multiple files, EPUB, docx, JSON lines files, and then web loaders like Cheerio, Puppeteer, Playwright, etc. So super handy, even a GitHub repo. So this is cool. So you can load directly from a GitHub repo. Super useful. Okay. So in general, that's what these document loaders do. Make it easy to load documents into the abstract document concept that LangChain is dealing with under the hood. And so here I just set up a directory loader to say, slurp up everything that's in this directory, and then used a text loader to say that it's of class text. And so it was literally, aside from the imports, 2 lines of code to get all of the data loaded in a nice way. So if you loop through it and then print, you'll get everything, which is what is happening here, just as a sanity check. So again, this is one of the reasons, by the way, that I found using Jupyter notebooks in particular and Kaggle to be so handy for this project is, you know, I'm coming to this as a data science, and parsing this kind of data is not my day-to-day job. It's not something I've done every day, but by decomposing the problem, into multiple separate steps, right? Like as the notebooks sort of encourage you to do by creating multiple cells, like one cell for each sort of atomic unit of work, if you will. It's been incredibly handy to be able to spot check my work, so to make sure that the outputs that I'm getting are exactly as I've expected, that the data is clean, that it's being written correctly, that the season numbers and the episode numbers all match up as expected, etc. It's incredibly handy. And then I just have this feeling, compared to just like your average application or infrastructure code, if you will, that once you have this notebook working and you save it and commit it to GitHub, it just feels a lot more stable to return to it and then quickly run all. It feels like it's a pleasant experience, essentially, as speaking from the developer perspective. So really enjoyed it and highly recommend using at least Jupyter notebooks, if not Kaggle, for projects like this, where there's a large bucket of work that is just getting the data right? Like figuring out, how do I scrape this? How do I parse it correctly? How do I format it nicely? How do I clean it? How do I sanitize it? How do I chunk it? In what, with what parameters and configuration do I do all that? And then once you have it, it's really nice to be able to just save it as a notebook and then come back at any point and run individual pieces as needed. And so, as I mentioned in the previous episode, or in the previous video, there's also a companion notebook to this. So there's 2 notebooks that I've just recently open sourced. One is this data bench, which is, as I'm calling it, so this Office Oracle data bench. This is what slurps information out from the wiki, does all the parsing, and upserts it into a Pinecone vector database, as we talked about. There's also this companion Office Oracle DB test notebook, and this is also open source, and you can see that essentially what it is concerned with is simply verifying and testing the data that's been inserted into my Pinecone index as embeddings. And so this is incredibly handy too, because without having to worry about the app itself, right, I can come here and have a very simple little test bench where I can write any query, turn it into an embedding, query my index directly, and then make sure that the actual documents coming back make sense. And you can see in this case they do. The question is, what did Dwight find in the ceiling? And that's a query across every season. So we're really, for performance on this task to be good, we're looking for a response that can factor in all of the times that Dwight has looked in the ceiling, or similarly has looked around somewhere in the office and found something that was meaningful enough that the user would query you about it. And so by spot checking this information, I can see that the documents that came back are in fact excellent matches, because they're talking about the situation that led Dwight to seek out what was in the ceiling, which was a bat. So This is just a really handy way to be able to come here and quickly test something, and notice that I am not wrestling with Webpack and PNPM and Node.js and TypeScript and refreshing and blowing away the cache and rebuilding the cache and serving the client bundle, etc., because I'm just operating on data. So in my experience with this one project, this was a winning pattern, so I highly recommend it. Yep, and so you can see at the very bottom for this test bench, I just have, I go all the way down to wrapping my existing vector store into a new database object that can be queried via similarity search. And so then I can ask from an actual retrieval QA chain that is wrapping an OpenAI LLM, which is GPT 3.5 Turbo 16K for the slightly larger context window. I can start to ask it actually complex questions that require full knowledge of the season or the series, if you will. And so that's what we're getting back here. If you were to consider across the entire space of the show, if I asked you to list some dangerous situations Dwight has caused, we're getting back exactly that across every season and episode. So this is a really nice pattern to have us, at least what's worked for me this first time is having one Jupyter notebook that's for the data science pieces, getting the data, cleaning it, sanitizing it, creating the actual index, upserting our embeddings, and then one companion sort of data workbench or test bench, if you will, and that's what this is. So both of these are available now under my GitHub. So there's the Office Oracle data bench, which is the data science piece, and then the Office Oracle DB test notebook, which is just that small testing piece that we just saw. So let's quickly hop back to here, and I'll finish talking through how this initial data science book works for loading our AI bot. It's important to note that I believe, although I haven't done it yet, but I'm pretty confident now, having done it with this project, that this same general pattern of finding a good source of comprehensive data and parsing it into the correct chunkings, embeddings, and then inserting it into a Pinecone vector database, or wrapping that with langchain's QA retrieval chain, and then asking an LLM to use that context and answer complex questions, gets you pretty far, if not all the way, to having any arbitrary AI chatbot that is performing any identity or answering to any identity, answering for any arbitrary corpus of knowledge. So it doesn't need to be, descriptions of this one random TV show. I obviously chose that in order just to have something to operate on for fun for this project. But this pattern, I believe, would be pretty effective in achieving an arbitrary AI chatbot that can speak to or answer questions on an arbitrary corpus of knowledge and information. So these helper methods here are just little functions I wrote that read the metadata from that. So as we talked about here, when the main routine writes the episode files to local markdown files, right? So this one is season 5, episode 23, title is Michael Scott Paper Company. These are the functions that get that structured data back out of the file name. And they're intended to be used during the main upserting loop, which we'll see in just a second. So in this next cell, we are installing and configuring TickToken, which is a library that can count tokens correctly, because tokens are not the same as characters. And in this next section, we're using the Pinecone SDK to check if our target index name, so this is the index I've used for this project. My AI chatbot name is the Office Oracle because he or she is answering questions as if they knew everything about the Office television series, which they do. And so there's this nice little check you can do using the Pinecone SDK to essentially say, if my index name is not in my current indexes, then create it. Otherwise, leave it alone. And so this pattern is similar if you've done idempotent programming in any other paradigm. The idea is that we want this notebook to be designed in such a way that if I come back to this 2 weeks from now and just hit run all, everything should work fine, or at least I should get some really helpful errors, such as you forgot to include your API key or something, or you didn't export your Pinecone API key correctly, or your environment is missing for this init call, for example. But otherwise, everything should just work. Like if the index does exist because the app is running and I've built the index and the app is using that index, we don't want to do anything to it at all. We just want to see, does it exist? And then, okay, we're done. In previous versions of notebooks similar to this, I've had, you can even have a variable that's like upsert needed and start off with false. And then, you know, you could even say under here, if we did need to do this, then we would say upsert needed equals true, and then key off of this later in subsequent cells in order to do like the upsert essentially. But just a quick demonstration to show that in general, the way that I think about structuring these notebooks is to make them as idempotent as possible, meaning that you can run it multiple times and you'll get the correct output or correct action on the world. And so in this case, if we already have our index, we don't want to delete it. Maybe you could consider having a separate cell that is just for deleting the index neatly, and then you either don't use run all or you just conditionally run that one. There's a bunch of different ways you could handle it, but just a tip that's kind of how I'm thinking about building these cells and these operations. I want them, whenever possible, to be completely idempotent. Okay, moving right along. So this next cell is setting up a langchain text splitter, and it is that job. It's the text splitter's job to convert our source text, which would be in this case the summaries from each wiki page, into chunks that make sense so that they can be handed off to the embeddings engine or model next. We also describe the separators, and we can tune our chunk size and chunk overlap. There's a lot of great videos that James Briggs, for example, has done on these already, so check out his langchain chunking videos if you want to go deeper on these pieces here. In the next cell, we're setting up OpenAI support for embeddings from within the langchain library again, and then we mention we specify the exact embeddings model we want to use from OpenAI, and we set up this embed object. This cell here is just a nice sanity check, so you can include plenty of these sanity check cells where, you know, again, it can be idempotent. It can, if the index doesn't exist, you could either silently fail here or silently return nothing or just move on. But if you do have the index and you run this, you get a nice little sanity check that talks about the number of dimensions for your index, how many vectors are currently there. If I were to rerun this now, it would say 500 something. And then finally, this is our main upsert loop. So this is the point at which we have gathered all the information and data that we want from our source. We've written it to local files that are in the correct format that we want. And now we want to loop through every one of those local documents, form the correct metadata that's going to be included in the embedding, and then get an embedding for that actual text and insert or upsert that embedding along with the metadata and ID for it into our Pinecone vector database store, so that in the future, when our app is queried by a user, then what we'll get is this guy answering very plausibly because he has access to everything he needs to answer questions, essentially. So this is following a similar pattern. If you look at any of the Pinecone examples, or even some of the Pinecone code in langchain library itself, this looping through records by enumerating them and also wrapping the operation in TQDM in order to get sort of nice CLI progress output can be really helpful, especially if, in this case, there were, the actual upserting did not take very long. It was maybe a handful of seconds because I didn't have that much data. If you were dealing with a whole lot of data, also in the past when I tried a previous version of this app, it didn't work, and I tried upserting every single line in the, every single spoken line in the series, then this can take a little bit longer depending on how the chunking breaks out, and so it can be nice to have this sort of little output here. But essentially that's what the cell is doing. It is looping through all of our locally processed and formatted, nicely prepared, cleaned data and turning them into records with metadata, with split text, right? That has a chunk and then text and then the metadata itself. And then that's being upserted into our Pinecone vector DB. And that's what allows the actual app itself, as well as our test bench Jupyter notebook, to make queries and get back semantically relevant information for searches. And that's what allows this AI bot, when paired with an LLM, such as OpenAI's ChatGPT 3.5 or eventually ChatGPT 4, to have a very intelligent response, right? That seems like it is a plausible agent, if you will, that has at least seen the office, if it wasn't present there for all the events, because that addition of the raw intelligence, if you will, of the LLM plus the actual factual information of the vector DB is a really pretty winning combination, and that's what leads to the outcome of the app being plausible, fun to play with, seeming like you're actually talking to somebody who was there, kind of thing.